Guys, in this video we're going to talk about the most interesting part of this calculus section, which is optimization. So what exactly does that mean? Well, we're always trying to be the best. Nobody ever wants to be second best. We want to be number one. Now, what that means is that we're often looking for ways to maximize profit or minimize production cost. We want to be the fastest, or we want to be able to finish something in the shortest amount of time. If you notice, all of these solutions to problems are extremes. If we can find a function that can model this phenomenon, then we can use the calculus that we've been learning in order to find the maximums or minimums that we're looking for. So let's look at a couple of examples of optimization. Okay, so in this example we have a rectangular plot of farmland enclosed by 180 meters of fencing material on three sides. The fourth side of the plot is bordered by a stone wall. Find the dimensions of the plot that enclose the maximum area. Find the maximum area. So we see in the solution here a diagram of the situation. We have the stone wall and the three sides of fencing enclosing a rectangular area. Okay, now one of the simple equations that we can use here to model the situation is the equation for the area of a rectangle. And of course we know that the area of any rectangle is equal to the length multiplied by the width, which is our first equation here. Okay, but now we have a second equation, and this second equation is what is known as a constraint. And it's very common to find these types of constraints in these optimization problems. We see that we have 180 meters of fencing material on three sides, and that poses certain restrictions on the domain of the equations that I'm going to be looking at. Let's look at the second equation that they have in the solution. 2w plus L equals 180. Now where does this come from exactly? Well, we have 180 meters of total fencing, and the fencing is the total from these three sides, which of course is W plus L. When we put this together in an equation, we get 2W plus L equals 180. We can isolate the variable for the length by subtracting the rest of the equation onto the other side. And now what we have is L written in terms of W. We can now replace that in our original equation for area, which is the function that we were trying to maximize. So we can replace L with 180 minus 2W. So the area is going to be given by 180 minus 2W, which is L, multiplied by W. We can then simplify this expression a little bit by applying distribution, and we have that the area is 180W minus 2W squared. To maximize this area, all we have to do is find the critical points by differentiating and setting it equal to 0. The derivative of this function is 180 minus 4W. When we set it equal to 0, we get a critical point of 45. Alright, now, is that this entire solution? Not yet. We have to verify that this is in fact a maximum. So let's take a look at the second derivative. When we find the second derivative of the function, we have that it's equal to -4. That means our function is concave down, and our critical point is going to be a relative maximum. So the length, which is given by 180 minus 2W, we can now replace the critical value that we found and find the actual length, which is going to be 180 minus 2 factor of 45. And when we figure that out, we get a result of 90. So our area is going to be the length, which is 90, times the width, which is 45. In other words, 4050. A 45 meter by 90 meter plot will have the maximum area. And what is the maximum area? 4050 square meters. Let's take a look at another example. Okay, this is an example that comes from the field of finance a little bit. It's more applied than the last one. Let's read it. The cost C of ordering and storing X units of a product is C of X equals X plus 10,000 over X. A delivery truck can deliver at most 200 units per order. Find the order size that will minimize the cost. So in this problem, we're going to be minimizing cost. Okay, let's see if we can identify the constraint. Here we have that the delivery truck can deliver at most 200 units per order. So this is going to be the constraint for this particular problem. Let's check out the answer now. C of X is given by this formula. In order to find the maximum, or the minimum in this case, we have to again find the derivative and find the critical points. So the derivative in this case is going to be 1 minus 10,000 over x squared. For the first term, we're applying a regular power rule. And for the second term, remember, we can always bring this variable to the top with a negative exponent and apply the power rule here as well. When we set it equal to 0, we can then isolate the x and we get two critical points. X is either positive or negative 100. Now remember that X is the number of units of a product. X units. Does it make sense to have a negative number of units of a product? I don't think so. So the only feasible critical point is X equals 100. Alright? Now the order must include at least one unit, and it can't be more than 200 because that's our original constraint. So we need to find the absolute minimum for this domain. And if we remember from our previous video, that means that we have to compare the relative minimum with the endpoints to see if there's an endpoint that is lower than our relative extreme. So here we can evaluate our function at the critical point and at the endpoints. So when we have 1 unit, which is our first endpoint, we have a total of 10,001 as our cost. Now our critical point, which is 100, when we evaluate it, we get a total of 200 as our cost. And finally, when we look at the other endpoint, when we evaluate the function at 200, we have a cost of 250. Now from these three values, our lowest value is at our critical point. So our critical point is not only the relative minimum, it's also the absolute minimum. Okay, so the minimum cost occurs when there are 100 units, and the minimum cost is 200. Okay guys, that's it for the examples. There's a couple more in your book that you can check out. They're very similar. Please watch out for those constraints and keep on practicing. Till next time.